Bismillah ar-Rahman ar-Rahim. The Doppler effect is a phenomenon where the frequency of an electromagnetic wave changes due to the relative motion between the source and the observer. The relativistic Doppler effect considered here is a consequence of the special theory of relativity and the Lorentz transformations. So our starting point, and in fact most of the discussion, will be about deriving the Lorentz transformations. An example of a communication system in which the relativistic Doppler effect is considered is the global positioning system and the other global navigation satellite systems. Consider two inertial frames, S and S prime. These are frames with a constant relative velocity between them. Frame S prime moves with velocity vector v, with components vx, vy, vz, as viewed from the frame of reference S. The coordinate axes in the two frames are parallel. In frame S, the time and space coordinates of a point are t, x, y, and z. In S prime, they are t prime, x prime, y prime, and z prime. The spatial coordinates are in the three-dimensional vectors big X and big X prime. It is assumed that the origins of S and S prime coincide at t equal to t prime equal to 0. Consider an electromagnetic wave source at rest at the origin in S. A wave is emitted at t equal to t prime equal to 0. The special theory of relativity is based on two postulates. The laws of physics are the same in all inertial reference frames. The speed of light in empty space is the same in all inertial frames. This postulate can be stated in a more general way. In every inertial frame, there is a finite universal limiting speed for physical entities. So according to relativity, observers in frames S and S prime see a spherical shell of radiation expanding outward from the respective origins with the same speed c. Non-relativistic physics does not admit a velocity which is the same in all reference frames. Here, the constancy of c plays a major role in deriving the Lorentz transformations, a consequence of which is the relativistic Doppler effect. In frame S, the wavefront reaches the point with the spatial coordinates x, y, and z at time t. The relation between t, x, y, and z is that c squared t squared is equal to x squared plus y squared plus z squared. That's the L to norm squared of vector x, which can also be written as x transpose x. We have something similar in frame S prime. C squared t prime squared is equal to x prime squared plus y prime squared plus z prime squared. This is the L to norm squared of vector x prime, which can be written as x prime transpose x prime. The most important thing to note here is that both expressions have the exact same c. The transformations we look for must be symmetric with respect to S and S prime. The relations between these four variables and those four must have the same form, whether we want to express t prime, x prime, y prime, z prime in terms of t, x, y, and z, or the other way around. The inverse relations are obtained from the forward relations just by replacing velocity vector v by minus v. In the Galilean non-relativistic transformations, we have x prime equal to x minus tv. To account for the constancy of the speed of light in empty space in all inertial frames, we split x into two components, x1 and x2. x1 is the component in the direction of v. x2 is perpendicular to v. We also have this minus tv. We assume that in relativity, x prime is this expression with x1 and this term tv multiplied by a velocity-dependent scaling factor gamma. To orthogonally project a three-dimensional vector onto the velocity vector v, we multiply the vector by this 3 by 3 matrix v transpose multiplied by 1 over the L to norm squared of v. If a vector is multiplied from the left by identity of size 3 by 3 minus this matrix, the vector is orthogonally projected onto the two-dimensional subspace perpendicular to v. To split x into two components in the direction of v and perpendicular to v, we write x as 1 over v transpose v, v transpose x, plus identity of size 3 by 3 minus v transpose times the scalar 1 over v transpose v times x. Gamma is a positive velocity-dependent real number. X prime is equal to gamma times this part plus this part minus gamma tv. We can write x in terms of x prime and t prime using the exact same expression, replacing v by minus v. Given that x prime transpose x prime is c squared t prime squared and x transpose x is c squared t squared, what is gamma? Let's write x prime transpose x prime in terms of x and t. This is x prime, and here it is after merging these two terms as identity plus gamma minus 1 times V transpose over V transpose V, all times X. X prime transpose is minus gamma T V transpose plus X transpose times this matrix, which is symmetric. When we multiply X prime transpose and X prime, we will have to multiply this matrix by itself. We have identity plus 2 times gamma minus 1 V transpose over V transpose V. When we multiply these two terms, we get gamma minus 1 squared. Then we have V transpose V transpose divided by V transpose V squared. This is just V transpose over V transpose V. 2 gamma minus 2 plus gamma minus 1 squared is gamma squared minus 1. The product of these two matrices is identity of size 3 by 3 plus gamma squared minus 1 V transpose over V transpose V. So when we multiply X prime transpose X prime, we get X transpose, this matrix times X. We also have gamma squared T squared V transpose V, noting that if we have two real vectors A and B, then A transpose B is B transpose A. When we multiply these two brackets, we also get minus 2 gamma T V transpose X plus gamma minus 1 V transpose V over V transpose V V transpose X. That's gamma minus 1 V transpose X. This bracket is gamma V transpose X. This quadratic form is X transpose X plus this is scalar. Then we have X transpose V times V transpose X. That's V transpose X squared divided by V transpose V. X prime transpose X prime is C squared T prime squared. X transpose X is C squared T squared. In frame S, if the wavefront reaches the point X, Y, Z at T, the speed of propagation is the square root of X squared plus Y squared plus Z squared over T, and this is equal to C. In frame S prime, the speed is the square root of X prime squared plus Y prime squared plus Z prime squared divided by T prime. This is also equal to C. This is our first expression, T prime in terms of X and T. This is X in terms of X prime and T prime, exactly in the form of X prime in terms of X and T, except that V is replaced by minus V, and so rather than having a minus sign, we have a plus sign here. We can merge these two terms. Then we can write X prime in terms of X and T. Simplifying, these two terms are minus gamma squared TV. From here we get X plus gamma squared minus 1 V transpose X over V transpose V times velocity vector V. These two terms go away. We can write this expression as a scalar multiplied by vector V equal to the vector 0, 0, 0. If V is not the all zero vector, which is the case of interest, it must be that the scalar is equal to 0. Dividing by gamma, T prime is equal to gamma T minus gamma squared minus 1 over gamma V transpose X over V transpose V. We will come back to this expression after obtaining gamma. Square both sides and multiply by C squared. We get a second expression with C squared T prime squared on the left-hand side. The right-hand side is in terms of X and T. We now have these two expressions. The first is derived by writing X prime transpose X prime in terms of X and T. The second is obtained by writing X in terms of X prime and T prime, then replacing X prime by its expression in terms of X and T. We now equate this part to that part. This is what we get if we move everything to the left-hand side to get an expression in terms of X and T equal to 0. On the left-hand side, we have a scalar times T squared. We have scalar times T. Then we have a scalar that does not depend on T. This expression is true for any positive T and any vector X. So the coefficients of this quadratic polynomial in T must be 0. The good news is that we obtain consistent results. If this is equal to 0, and this is equal to 0, and this is equal to 0, we get that gamma should be equal to 1 over the square root of 1 minus the L to norm squared of velocity vector V divided by C squared. We got this expression for T prime. Now we know what gamma should be. Here are the Lorentz transformations. To express T and big X in terms of T prime and big X prime, we just change these minus signs into positive signs. We can write these two expressions using a 4 by 4 matrix. Here we have the scalar gamma. Here we have the three-dimensional row vector minus gamma over c squared v transpose. This is the three-dimensional column vector minus gamma v. This block is the 3 by 3 matrix identity plus gamma minus 1 v transpose over v transpose v. The consequences of the Lorentz transformations include time dilation and length contraction, but let's focus here on the relativistic Doppler effect. Consider a monochromatic plane wave in frame S. This is a complex amplitude A, e to the I k transpose x minus omega t. The frequency is omega. K is the wave vector with three components kx, ky, kz. This inner product is kx times x plus ky times y plus kz times z. The norm of vector k is 2 pi over the wavelength lambda. Lambda is equal to c over the frequency in hertz f. Lambda is equal to 2 pi c over omega. Omega over the norm of k is equal to c. While the speed of light c is the same for all observers, the frequency omega and the wave vector or propagation direction k depend on the observer. So in frame S prime, the wave has frequency omega prime and wave vector k prime. Vectors k and k prime are normal to the wave fronts with respect to frames S and S prime respectively. The components of k prime are kx prime, ky prime, and kz prime. Taking the phase to be invariant, we have k transpose x minus omega t equal to k prime transpose x prime minus omega prime t prime. We can write this equation as k transpose minus omega times the four-dimensional vector xt equal to k prime transpose minus omega prime times the four-dimensional vector x prime t prime. The next step is to write down this vector in terms of the vector x prime t prime. This part is equal to the four-dimensional row vector k transpose and minus omega times the 4 by 4 matrix of the Lorentz transformations times the vector x prime t prime. Since this is true for all x prime and positive t prime, then this part is equal to that one. Take the transpose of both sides. On the left-hand side, we get the four-dimensional vector k prime minus omega prime. On the right-hand side, we get the transpose of this matrix multiplied by the four-dimensional column vector k minus omega. Multiply both sides from the left by this diagonal matrix. The main diagonal elements are 1, 1, 1, and minus 1. When this matrix is multiplied by this vector, we get the four-dimensional column vector k prime omega prime. If this diagonal matrix is multiplied by a matrix with 4 rows, we get the same 4 rows except that the bottom row is multiplied by minus 1. Thus, when this matrix is multiplied by this 4 by 4 matrix, the top 3 rows are left unchanged. The fourth row is multiplied by minus 1. Gamma v transpose and gamma are changed to minus gamma v transpose and minus gamma. If a column vector is multiplied by a matrix from the left, the matrix vector product remains the same if the sign of the last element in the vector is flipped and the leftmost column in the matrix is multiplied by minus 1. So we can rewrite this matrix vector product using the vector k omega. Now we need to multiply this column by minus 1. The fourth column in the matrix becomes minus gamma over c squared times vector v and gamma. We have now established a relationship between k prime and omega prime on the one hand and k and omega on the other. We can derive several relations from here, including a relation between the frequencies in the frames S prime and S. Omega prime is minus gamma v transpose k plus gamma omega. Recall that gamma is 1 over the square root of 1 minus the L2 norm squared of vector v divided by c squared. In this expression, we have an inner product between the wave vector, the vector normal to the wave front in frame S, and the velocity vector v. We can write this inner product as the norm of v times the norm of k times cosine the angle between them, as viewed in frame S. So omega prime is gamma, between brackets omega minus the norm of v times the norm of k times cosine theta. If we take omega as a common factor, this becomes 1. This term is divided by omega. The norm of vector k, which is 2 pi over the wavelength, divided by omega, is 1 over c. So omega prime is equal to gamma omega, 1 minus the speed over c times cosine theta. Omega prime depends on omega, velocity vector v, and the angle between v and the direction of wave propagation. This is the relation between omega prime and omega when we write gamma explicitly. Note that we have a transverse Doppler effect. if the angle theta is equal to 90 degrees, which means that in frame S, vectors v and k are perpendicular, still omega prime is different from omega. Specifically, in this case, omega prime is equal to omega over the square root of 1 minus the speed squared divided by c squared. We can use this expression to derive more relations. In S prime, the wave vector k prime is equal to this 3 by 3 matrix times k. That's k plus gamma minus 1 v transpose k over v transpose v times vector v. We also have minus gamma omega over c squared v. Multiply both sides from the left by v transpose. So v transpose k prime is equal to v transpose k plus gamma minus 1 v transpose k. Then we have v transpose v over v transpose v, that's 1, minus gamma omega, the norm of vector v squared divided by c squared. Combining these two terms and taking gamma as a common factor, v transpose k prime is equal to gamma v transpose k minus the speed squared over c squared times omega. We can use this expression, for instance, to obtain the angle between velocity vector v and wave vector k prime. This inner product is the L2 norm of v times the L2 norm of k prime times cosine theta prime. That's the angle between v and k prime. This is equal to gamma, between brackets, the L2 norm of v, the L2 norm of k, cosine theta, minus the L2 norm squared of v over c squared omega. The speed of light c is the same for all observers. C is equal to omega over the norm of k. C is also equal to omega prime over the norm of k prime. We can replace this by omega prime over c, and that by omega over c. V is non-zero. Dividing both sides by the norm of v, we get that omega prime cosine theta prime over c is equal to gamma omega over c cosine theta minus the speed over c squared omega. Then cosine theta prime is equal to gamma omega over omega prime cosine theta minus the norm of v over c. We have this ratio. Thus cosine theta prime is equal to cosine theta minus the norm of v over c divided by 1 minus the norm of v over c cosine theta. This is the relation between the angle between v and k prime in terms of the angle between v and k. Last thing, let's go back to the expression relating omega prime and omega and write 1 over this square root using the Taylor series. We get that omega prime is equal to omega, between brackets 1 minus the speed over c cosine theta. 1 over the square root is 1 plus the speed squared over 2c squared plus 3 times the speed to the power 4 over 8c to the power 4 plus a function of the order the speed over c to the power 6. Because of this term here varying as the square of the speed over c, sometimes the relativistic Doppler effect is referred to as the second order Doppler effect.